Welcome to The Explainer. Today we are uncovering the hidden motivations of the universe's absolute tiniest building blocks. Because when you really think about it, atoms are kind of like restless entities on this universal quest. They're constantly searching, combining, reacting, and doing whatever it takes to achieve the ultimate atomic Zen state, which is stability. And how exactly do they find this peace? Well, through the incredibly dynamic world of chemical bonding.
Okay, let's dive into this and start with literally the most fundamental question we can ask. Why do atoms combine in the first place? Out in nature, under normal conditions, the only elements that are perfectly content just hanging out all by themselves are the noble gases. They're the introverts of the periodic table. Every single other atom is out there frantically looking for a partner. But why?
Well, a chemical bond is simply the attractive force that holds these constituents together. You can really just think of it as nature's brilliant way of lowering the energy of a system. Every system in the universe naturally wants to move toward a lower energy state so it can finally relax and be stable. And bonding? That's exactly how atoms achieve that much-needed long-lasting stability.
So, here's our roadmap for today. We'll start with the quest for stability, explore covalent bonds, and calculate formal charge. Then, we'll look at breaking the octet rule, transferring electrons and ionic bonds, and wrap the whole thing up with bond parameters and resonance.
All right, jumping right into Section 1, the quest for stability. And this whole section is governed by one of the most famous concepts in chemistry, the octet rule. So back in 1916, scientists Kessel and Lewis independently cracked a major code. They realized that the inertness, or, the chemical laziness, of noble gases was the key to the whole puzzle. Noble gases naturally have an octet, meaning 8 electrons in their outer shell. Kessel and Lewis theorized that atoms combine specifically to hit that same stable octet. Just a few years later, in 1919, Langmuir refined the idea and officially introduced the term covalent bond as a way to reach that magical number 8.
Which brings us right into Section 2, sharing electrons, or covalent bonds. Basically, this is nature's collaborative solution. Think of atomic bonding almost like a social interaction. Covalent bonds are all about cooperation. Atoms are literally sharing pairs of electrons so they can both attain that stable outer octet. Now, this is totally different from ionic or electrovalent bonds, which involve a completely dramatic transfer of an electron from one atom to another. So simply put, covalent is sharing and ionic is taking.
Now, to actually visualize this whole sharing process, we use what are called Lewis dot structures. Imagine we're at a whiteboard right now. First, you just add up all the valence electrons available from your combining atoms. If you're dealing with an ion that has a net negative or positive charge, you just add or subtract electrons to match. Then, you distribute those electrons as shared bonding pairs between the atoms. And finally, you hand out the rest to make absolutely sure each bonded atom gets its stable octet of 8.
But what happens when things get a little mathematically complicated? Let's move into Section 3, calculating formal charge. I like to call this the visual accounting of chemistry.
See, when a whole polyatomic molecule or ion has a net charge, that charge isn't actually just sitting on one single atom. But for our accounting purposes, we assign a formal charge just to keep track of who owns what. So the crucial point is this incredibly simple 3-step formula. You take the total valence electrons the atom would have in a free, isolated state, subtract all its non-bonding or lone pair electrons, and finally, subtract exactly half of its shared bonding electrons.
Now, why does this matter to you? Why do we even bother doing this math? Because it helps us predict reality. The lowest energy structure, which remember is always the most stable and realistic one out there in nature, is generally the one with the smallest formal charges on its atoms. So this math directly tells us how a molecule actually prefers to exist in the real world.
But of course, nature absolutely loves throwing us a curveball.
Welcome to Section 4, breaking the octet rule, the exceptions to the law.
Now, what's really interesting about this is that the ultimate rule of chemistry, the octet rule, actually has some pretty notorious rebels. There are 3 main types. First, the incomplete octet. Elements like lithium and beryllium can actually be perfectly stable with less than 8 surrounding electrons. Second, odd electron molecules like nitric oxide. They just physically cannot pair an odd number of electrons up into neat little 8s. And third, the expanded octet. Elements in and beyond the 3rd period of the periodic table, like sulfur in SF6, have extra d orbitals available, so they can happily hold way more than 8 valence electrons. They blatantly break the rule, and they are completely stable doing it.
Okay, let's shift our focus over to the other major bonding style in Section 5, transferring electrons, or ionic bonds. This isn't about sharing at all, this is all about the power of attraction.
If covalent bonds are a friendly partnership, ionic bonds are a flat-out dramatic transfer. One atom completely loses an electron to become a positive cation, and the other one snatches it up to become a negative anion. This massive electrostatic attraction creates these beautiful, highly orderly three-dimensional crystalline structures, and this really grounds our microscopic concept into macro reality. What we're looking at is the rock salt crystal structure of sodium chloride. Yep, that's literally just everyday table salt.
And just how stable is this crystal structure? Well, when 1 mole of solid sodium chloride forms its crystal lattice from separate gaseous ions, it releases a massive 788 kilojoules of energy. That is a huge amount. We call this lattice enthalpy, and it's the true secret to the stability of ionic compounds. The more energy they release when they lock together, the more deeply, profoundly stable the crystal becomes.
All right, we are now entering our final stretch, Section 6, Bond Parameters and Resonance. This is where we focus on measuring the invisible. We know these bonds are there, but how do we actually measure the strength and the shape of these microscopic connections?
And this brilliantly illustrates our first critical parameter, bond length. By using advanced techniques like X-ray diffraction, scientists can measure the exact equilibrium distance between the nuclei of 2 bonded atoms. Basically, each atom contributes its covalent radius to the total distance. It is a highly precise physical measurement of their chemical closeness.
Let's just rapid fire through the toolkit scientists use to map these molecules out. We just saw bond length. Next up is bond angle, which tells us exactly how the orbitals are distributed around a central atom, giving the molecule its specific 3D shape. Then there's bond enthalpy. That's the exact amount of energy you'd need to physically break the bond apart. And finally, bond order, which is honestly just the number of bonds between 2 atoms. Like, is it a single, double, or triple bond?
And what you really need to take away from this is how deeply intertwined these parameters are. A core rule of thumb is that with an increase in bond order, bond enthalpy increases and bond length decreases. It makes perfect logical sense when you think about it. A triple bond holds atoms much tighter together, making the physical bond shorter, and it requires significantly more energy to break apart than a single bond. It's a tighter, much stronger grip. But here is the final, completely fascinating twist in our atomic narrative: resonance. Sometimes one single static drawing just isn't enough to capture reality. Take ozone, for example, O3. When we draw its Lewis structure, we're forced to draw one single bond and one double bond. But experiments prove that both oxygen-oxygen bonds in ozone are actually totally identical in length. This means ozone exists as a resonance hybrid. It's this fluid, continuous combination of multiple structures that, when blended together, accurately describe what the molecule is actually doing.
Which leaves us with a pretty provocative thought to close out on. If a basic molecule like ozone doesn't even exist as a fixed, rigid structure, but rather as this fluid hybrid of shared electrons, how fixed is our physical understanding of the universe around us? The rules of chemistry guide us for sure, but the molecular world is so much more dynamic, collaborative, and beautifully quantum than a simple whiteboard drawing could ever capture. Thanks so much for joining me on this explainer, and hey, keep questioning the structures around you.